Hello and welcome to this presentation of ArcGIS API for JavaScript, a look under the hood. I'm Jan Caben and I'm joined with Yaron Fine and Matt George. We are three engineers on the JavaScript API. In this session, we like to talk about subjects that we worked on. And this year, we are talking about modernizing the API globalization. Yaron will talk about layer blending and effects, and Matt will talk about clustering. Let's jump into modernizing the API globalization. Modernizing the JavaScript API was completed at 4.18, and the goal was to distribute the API as a collection of ES modules that you can easily install using NPM. And as part of the process, we had to replace a lot of internal libraries, like Dojo 18N that was used for globalization. Used specifically for date and number formatting and parsing, but also for localizing widgets. And the localization files, they are loaded by Dojo 18N on demand using an AMD loader plugin. So maybe you are not familiar with AMD loader plugins. So they are used to load other resources than JavaScript files, like HTML, CSS, and text files. It is a very practical pattern. It does look like a normal AMD module import with a specific syntax using the bang sign. And it's also a very practical pattern that is implemented by other build tools like Webpack. Webpack has loaders, for example. But the problem of this specific module syntax it's that you depend on a build tool to understand them. And unfortunately, Dojo 18N is not supported outside the Dojo and require.js AMD loaders. So this module, an AMD module written like this, would not work with Webpack, for example. And that's why we had to remove it. The replacement is Esri Intl. It's used for date and number formatting, which is built on top of the native ENTL library that is part of web browsers. And this part was released in 4.12. And then we developed a custom solution to load localization JSON files for widgets, and we released that in 4.16. So you can look at the API reference of this library if you are interested in using it. It's available on the SDK under the Esri folder, ENTL, and you will have all the information on how to properly format date and numbers, but also all the methods to localize widgets. Let's jump right into demos to show how to use ENTL date-time formatting. So this demo is a little wizard to be able to play with the different options of ENTL date-time format. So to create a date-time format in JavaScript, you can just instantiate this object, date-time format. You pass the local and an option object with the configuration how to format. So in this particular case, I said that I want to have a long weekday written, as well as the year, months, and day, hours, and minutes. But then I can change, for example, from a long weekday to a short weekday, or not display it at all. And I can remove all the different components and keep just the time, so I can format just the time of this particular date. What is nice with the ENTL is that you can specify the local and the language, but also the culture. So for example, in US English, you will format 2 p.m. like this, but then in UK, you would format it as in 24-hour cycles. So ENTL adapts both the language and also the culture. It's going to be the same in French. So it's really, really powerful. You can, of course, override these components by forcing 2 p.m. the hour cycle, for example. Number format from ENTL is also similar. You can specify the local and different options. So the basic ones is really the number of significant digits that you want to be able to display. You can control the notation, so by the standard notation here, or the scientific notation, engineering, or compact. And then a powerful feature is the style. So by default, it's going to be formatted as a decimal, or you can set it to percent to display percentages, or in currency. So you can specify the currency and also how you want to display the symbol. So here we are in US dollars, but then I can switch to euro and then display by either the symbol or the code or the name. And you will see that it adopts a different position. And recently they added unit. So to display in meters or in degrees Celsius. And same, you can have a very long unit display or just a symbol. So date and number formatting is handled by the native Intl API. It has IE11 support, but not for everything. And it has, like I showed, very fine-grained control over the formatted output. It's not a finalized API. The consortium is still adding new options. So recently they added date style and time style to more easily format the dates and times with shortcuts like, okay, I want to have a long date or a short date format. They also added the notation option, so scientific, compact, and so on, and the style unit to be able to format units in meters per second, and so on. One of the issue using this API is that we are more exposed to bugs in the web browsers, and for this we, when someone reports an issue with localization like this, we just push those issues into the bug tracker, for example, from Chromium, if the bug is with Chrome. But usually it's a much better solution than using something custom. Let's now take a look at the solution we developed in-house for handling translations of the API widgets. I built 3 demos to go through the main features. So in this first demo, you can see like that I have a drop-down where I can select different languages, and then on the right side I have a translated widget. So here I have Bonjour le monde, but if I switch to US English, I have Hello World. You can see that everything refreshed as I changed the language. So the way it works here is like we have our application object that is created with a container, which will be our element where to render. And then we have our render function, which is showing some JSX here, where I have a div, and inside I have my message, my hello world message. So before starting rendering, we need first to fetch the local, and we do that asynchronously by calling this function, update message bundles, and then we kick off the rendering. And what we do is after, if the local changes, we do the same process. We call again update message bundle, and then we schedule a new frame for re-rendering. So this feature is very handy because the widgets can be relocalized at runtime. Let's take a look at update message bundle. It's a function where we get the language from the current local. So we will get, in this case, EN. And then we are going to fetch our JSON file in the folder. So en.json or fr.json. And then we store that as a property, messages, and then we schedule a new frame to re-render. Now, as a second step in this application, I have abstracted the core principle of fetching message bundles and kick off the rendering into a base class called widget. And each subclass is free to add bundles information to specify which bundle to fetch. So for example, message.json, for example, and in which property to store the result. Now in my subclass application, I extend widget, and I just say, okay, I want to fetch the bundle name called application and store the result into the message property, and then fetch the common bundle and store it into the common property. The advantage now is like in my render function, I have access to both bundles, and if I switch to French, I will see two strings updated. If we take a look at the different bundles, we have application.en, application.fr, and same for common. So that's the second step. And now, finally, for developer convenience, we have been using TypeScript decorators. So if we recall, we have this bundle info where we push information which property to store which bundle. Now with TypeScript decorator, I can develop a decorator called message bundle where I specify what is the bundle name, so application or common, and then I decorate directly the property on top of it. So how to create those decorators? So in TypeScript, a decorator is looking like this. It's a function, and then you pass your argument, and then this function will. So this function is called like this: message bundle common, and my function returns a property decorator, which is a function that will be decorated, that will be called with the target, which is the class. So in this case, it will be called with application, and the property that is being decorated. So in this call, it's going to be common. So now I can get the prototype of the application and push inside the prototype the bundle info. So with the previous bundle info and my new property. So now every time this decorator is called, it will add to the application bundle to the bundle infos that is owned by the widget. So then when the widget starts, it will find in its bundle info everything to localize. So it's very handy because it hides the complexity and the mechanism that are happening under the hood. I hope this gives you a good overview of how the localization works with the JavaScript API. To finish here, I have some resources listed in the slides. We have the link to the Esri ENTL documentation, a link to the ENTL reference documentation on the MDN, a link to the demos that I demoed, and also a link to the Chrome project issue tracker that is dedicated to internationalization. Thank you.
Hi, my name is Yaron Fine. I'm a developer on the JavaScript API. I'm part of the team who builds the 2D rendering engine for the API. Today I'll be talking a little bit about layer blending and layer effects. I'll talk about what it really means and how it works, how it came to be, and maybe try to show an example that take advantage of layer effects. So in terms of background, it all really started with Opacity. When we just started implementing the API, we apply the opacity per feature, meaning that when we render the feature, we simply apply the opacity for each fragment. It was easy, it was fast. We didn't really have to do much, but then realized that the cartographic outcome is not really where we need it to be. The reason for that being that in areas where features overlap, the opacity is changing. And of course, the more feature overlap, it becomes more and more opaque. And if, let's say, a user wanted 50% opacity in area which is very dense and features really overlap, it ends up being completely opaque. So that is really not the desired outcome. So we try to figure out the proper way to handle that, and we realize that in our case, the best way is to deal with opacity is to use what's called a render target, or in the WebGL world, it's called a frame buffer object. The technique is to render the layer without any opacity onto that render target. Then blit the content of that frame buffer object, or what's called the color texture, on top of the map with the desired opacity. This way, we end up with exactly the result that we're looking for. In this case, we see that blitting the features with 75% opacity on top of the base map, and indeed the outcome has 75% opacity. Schematically, this is how it looks. We render the layers. We render, of course, from the bottom to the top. And then for each layer, we check, does it have opacity? If it does not, then we render it directly onto the map or the map display. If it does, then we render it onto the render target and then blit it on top of the back buffer with the desired opacity. When we, after we implement that, we had a eureka moment. We realized that, hey, what we're really doing is what's called full quad drawing. And we're doing, right now, we will start with just applying the opacity when we blit the information on top of the map display. But then we realize, hey, we can do so much more than just that. And this is really what led us to think that we can start incorporating the additional blend modes and the layer effects. Starting with blend modes. Blending is really defined as the way in which fragments that generated from a given draw operation are mixed with the background. Well, think about fragments really as pixel colors. Traditional WebGL blend modes are somewhat limited. Colors could be really washed out, and you can see here in the bottom where the image from on the left uses the standard opacity with thematic data rendered on top of a elevation data. On the right, we render the same data, but we apply a multiply blend mode, and you can see how the terrain all of a sudden popped. So that is, basically generating a much nicer cartographic outcome. Those blend modes, those additional blend modes defined on a Canvas API, and it is way more rich in terms of what OpenGL provides out of the box. In general, those blend modes are divided into two groups. There's the composition blend modes, where we define the behavior between two groups of items, meaning that if the data overlap, we only render the target, or only render the top, or we exclude the top, or and so on. And of course, we also consider the overlapping area and figure out how to mix those colors. Multiply, of course, is just one of the blend modes, but there's way more. There's hue, there's saturation, there's a bunch of them that we support. We rely on what's called the Porter-Duff composition operator. If I open it in a different page, you can take a look. This is how it define the different areas, and then the blend equation define the behavior for each area. If there is overlap, if there's no overlap, and so on and so forth. Going back to the slides. So, schematically, the way we are doing the blending, it's very much similar to how opacity works. When we render the layer, we check does a layer has opacity, or a blend, or effect, or all of them, of course. Then at that point, we simply render the layer onto a frame buffer object. And then when we're doing the processing that we need, and then when we blit the frame buffer on top of the map, then we're applying in this case, the opacity. And we multiply we combine the colors from the back buffer and the color from the map according to the desired blend effect. And since we have already given the example of multiply, in here you can really see the equation, how it really works. This is really the math behind that is used in the shader to do the blending. One thing to note is that when we're doing the map composition, when we compose the layers one on top of each other, the blend mode is the last per pixel operation that is being applied. Effects. Effects, very much like the blend modes, are sort of a post-processing effect. The idea is that after we render the layer onto the render target, and before we're applying the blend, we have room to apply additional effects. It is inspired by the CSS effects. You can look at also Adobe Photoshop or GIMP filters, whether it's bloom or drop shadow, emboss operation, sepia, grayscale, and so on and so forth. And it really helps. Traditionally, at least, users used to print the map or print an image, bring it over to Photoshop or other image processing software, and then apply the effect that is desired. And basically what we're doing is we're applying user to do the same thing, but in real time. We really distinguish between three types of effects. There is what effects that are driven by convolution, such as blur, bloom, drop shadow. There's colorize effect, like sepia, brightness, contrast, grayscale. There's geometric effects, like morphing the image or applying a wave effect or distortion. And there's a bunch of others that I'm not going to, I don't have enough time to list right now. And then looking at an example, this is an example that I've written for the purpose of this talk. Applying applying effect. And by the way, effect don't necessarily need to be applied to static image or static data. In this case, it's going to be applied to dynamic cars that is really implemented as a custom layer. Maybe I should start with the demo to show how it works. Here, let me step out of that. Here is the page with the demo. It's actually built as a series of demos. The first one simply shows how to render dynamic cars. The second one also implement the post-processing, which is the highlight. And the third one is a worker. By the way, at the end, I added some links to the public repo. So if anyone wants, they can you can take a look at the code. You can try it. You can modify it and use it as you wish. I'm going to launch a demo. And let's start. The demo for this, the data for this demo is streamed by imagine it's like a synthetic or like a fake service that streams the data through a WebSocket. It is consumed by the layer here. Now let me connect, and you can see the cars rendering. Notice, by the way, how fast relatively they are moving. So these are 10,000 items, cars in this case, in the United States, where generate the data based on the roads feature service. And then we can also apply the post-processing, which is the highlight. In this case, the service is choosing a random set every few seconds, mark those as what's called active. And then the implementation is rendering them with the those highlight, cyan highlight with the red outline. So of course, there's more than one way to implement highlight, but we've chosen, for the sake of this demo, to implement it with the as a post-processing effect. So how does it work? Going back to the slides. So how we're gonna do this? The idea is that we render the cars as usual. Then, in order to render the highlight, we're only rendering the cars that are marked as active. What it really means, we're clipping the cars that are not active and render those onto a frame buffer object. And when we render that, we're rendering it with a factor. Think about it as we're dilating the shape of the cars. So then the content of that frame buffer object has only the cars that are marked as highlighted. Then we apply a series of blur operations first at the horizontal direction, then at the vertical direction. And then eventually what we're doing, we're bleeding that frame buffer object on top of the other cars while using the alpha channel to color the information. This is how we're getting this cyan output and also generating the red outline. I think it'll be a lot easier to see the process in a WebGL debugger. Let me open that. I capture here a frame. Notice in the background it is rendering the base map, which is a vector tile. And we start with just rendering the cars. And this is the frame. Notice it's rendered to the current render target, which is think about it as the display display output. We're starting with, of course, transforming the cars. And then we transform each vertex to the right device or normalized device coordinates. Then we extrude each vertex to the right position, and then we eventually sample the colors from the car's texture, and then it gets rendered onto the display. The next step is to render those same cars, but only the ones marked as active onto a dedicated frame buffer. Notice that notice the number is different here. In this case, it's frame buffer number 0. That is the one that we use it dedicated for the effect. Again, I'm going to look again at the vertex shader. Notice that it's almost identical to the one I showed before, but notice that I added that there's a define edit here, highlight path. So it goes into the defined section. And what it really does, it looked at the property indicating whether the given car is active or not. The value is 0 or 1. When the value is 0, the step function gives us a value of 1. And what that would do is would increment the delta z. And with that value, when we add it to the position, it's going to push it beyond the clipping plane, meaning it caused that vertex to be clipped. So effectively, what we're going to end up, we're going to only maintain those vertices for the active cars. The rest are going to simply get clipped. Well, there's another things that we've added. There's an element of time, of course, and a factor that we apply. And we use that in order to dilate the cars, which we need in order to generate the desired shape that is constantly changing over time. So once we've done that, then we're running through the steps to blur the image. So the first step is the horizontal blur. Here, what you're seeing here is the fragment shader for the Gaussian blur that is being applied. The next step would be to apply the vertical blur paths. By the way, we divide into a vertical and horizontal just because it's faster. If we are applying the blur or the convolution in one dimension at a given point. Once we've done that, then we can run the code that actually what's called the full quad operation, or doing the screen space blit of the content of the blurred image. And this is where we're actually coloring the halo. You notice that we're trying to figure out, we get the alpha from the blurred image, and we're trying to see whether we're on the edge of the halo, and of course that would be used, to generate the red outcome. Notice that we're only coloring the red component in that case. In the other case, we're generating the cyan color, and we're using the alpha component. And once that is getting blit, eventually, that is going to be added to the screen, and then you see the highlighted cars on top. Going back to the presentation. So that is really the technique behind it. I've added the all the links that I used here. These are the public GitHub repos. One for the service that stream the data or the car data. The other one is the series of implementation that custom layer that render the cars and also show the highlight technique. These are links to our API referring to the blend modes and the effects that are available. I added a link to the W3 blending spec and also to the NVIDIA OpenGL extension, which really defined the list of blend modes that we're supporting and defined the algorithm for each of the blend modes. I'm going to now hand back the talk to Matt to complete the presentation. Thank you.
Hi, I'm Matt George, a rendering engineer on the JavaScript team. And like Jan mentioned, I'm going to talk about our clustering implementation in 4X. So to start us off, what is clustering? Well, clustering is a type of feature reduction that provides a kind of density visualization, typically for displaying many points on the screen at any given point in time. A key thing to note about our API versus other mapping APIs is that our API uses an inferred renderer to drive the visualization. That means that when a user enables clustering for a given layer, we go in and extract out the aggregate fields and symbology from the underlying renderer type. The nice thing about this is there's no additional configuration needed, and it helps to keep both in sync. That brings us to some of the design goals we had when designing clustering for the 4X API. The first of these is that it must be incremental. When dealing with a large number of features, it's really not a great experience to have to wait for all of the data to download up front before seeing anything happen on the screen. And this becomes an even bigger issue in 4X, where we support rendering a far larger number of features than we could in the past. So as a requirement, we must be able to compute and update clusters on the fly as we download them. Another design goal that falls into play with this is that it really has to be quick. From the onset, we really wanted to make sure that the interaction between clustering and feature filters was really as good as it is for features by themselves. And because of that, we had to make sure that index creation had these really strict time requirements in order to allow for immediate reclustering in response to changes in the underlying client-side filters. And because clustering is this sort of density visualization and is great for allowing you to visualize a massive number of points, we really wanted to remove the 3x feature limit requirements that existed previously. And that gets us to the problem itself. How do we go from this to this? And when we talk about clustering, the basic idea is actually pretty simple. First, we select a random point. Then we find every other point within some cluster distance of that first selected point. We merge those points into a cluster, and then we repeat the process for points that have not yet been merged. And well, you might be saying, well, that second part you glossed over, isn't that quite expensive, and isn't it global as well? We would need all the points up front in order to compare each point to every other point. And yes, you would definitely be right. And like we mentioned in the onset, right, that's just not going to work with our design goals. Unfortunately for us, this is a pretty common computer science problem. Especially in spatial programming, to speed up this sort of neighboring calculation, we're going to need to build a spatial index so that we can immediately reject points that we know could never potentially be a neighbor. When we're creating a cluster, we only want to compare points that fall within the spatial index cells that fall within that cluster region. And this will help us to avoid this sort of n-squared computational complexity that we might otherwise run into. And so a geohash is what we use to solve this. So what is Geohash? Geohash is a public domain geocoding system invented in 2008 and essentially encodes geographic information into a short string of letters and digits. The way it does this is that it basically includes an alternating series of recursive subdivisions. And for any given geographical point, you basically state for each recursive subdivision whether or not it is left or right of that subdivision. And for every geohash level, you will have 5 bits, 3 of which encode the longitude and 2 of which include the latitude or vice versa, depending on the level. So those codes will alternate for every level. And that's why if we go to the next geohash level, as you see here, we can see that the rectangle actually flips and that we now have basically the transpose of what we had previously. And we include the previous prefix, right, which was 9. As well as including, another grid for this next level of detail. And if we think about this, Geohash is really just a kind of grid encoding, where each level has 2 or 3 bits for the longitude or latitude. The bit structure is the same as any other power of 2 grid. What differs here is really how many bits are in a given level. Importantly, we can interpret a Geohash key with respect to the power of 2 levels just by unpacking that base 32 string. So this is a pretty important idea here, and I'll go in a little more detail about what exactly this means and how exactly a Geohash key is encoded a little bit later in the presentation. But before that, let's go over our clustering algorithm again, this time taking into account the Geohash and the spatial index that we've now constructed in order to detect future neighbors. So again, we're going to start off with our input point layer that we're going to want to cluster. From that, we're going to compute each point's Geohash, placing them into their corresponding cells. After we've divided points into cells, we're going to generate statistics on each cell, including at a minimum the count and centroid of each cell, but depending on the renderer, we may have a variety of aggregate fields and aggregate values that we have to compute as well in addition to this, and we would include those statistics in the cell totals here as well. From that, and this is also a point that's a little bit different than before, we're going to construct a grid of a cluster radius size over those cells, and we'll use this to actually construct the clusters. And from here, we're going to merge cells that fall within these cluster cells to compute clusters. And we can see here, right, that we have exactly the same result as before, right? We have our clusters, our input point layer, our final output, and everything's good. The end, right? Presentation over. Well, not quite. So unfortunately, we created this cluster grid abstraction in the last walkthrough here. And the reason we do this, right, is because we want to be able to create clusters dynamically as we load more data. So it's very important that we don't have this sort of first point problem, right? We don't want the map to be different depending on where a user has initially loaded things. We want things to eventually converge to look the same. And because of that, we need to be able to deterministically determine where these cluster sort of aggregation bounds are going to be. However, what if this grid does not match? What if we don't have sort of this perfect thing where cells fit perfectly within these cluster grids, which, by the way, is going to be overwhelmingly the most common case? Well, then we run into the problem that we have here on the right, where we suddenly have this need to actually know the neighbors of a given Geohash cell. Because, right, if we look here and we look at the cluster in the top rightmost position, the cluster bounds associated with the cluster in the top right position, we can see that almost more than half of it falls on these cells that we're not even intersecting on the screen, right? So we actually have to pull up the neighbor of 9, which is going to be D in this case, and we need to be able to determine which Geohash cells are basically the neighbor of 9. So we need to know that DP in this case is going to be the neighbor of 9Z. And, just looking at it, right, these are 2 strings, how do you even do this? How do you even compute what the neighbor of 9Z is? Well, this is actually a interesting problem, because while it is very easy when you share a prefix to determine whether or not something is near you, it is very hard to determine whether or not things neighbor each other when they do not share a prefix. And as we can see here, that is very important because 9Z is going to be closer to DP, which does not share a prefix, than it is to, say, 9E, which it does share a prefix. So how is this typically handled? Well, if you go on GitHub, you'll probably find code that looks something like this. And while this code is definitely really clean, there are going to be some pretty serious performance issues with something like this. We can see that there's a bunch of string operations. We need to build up tables of every possible neighbor, a table of borders. We're going to have to do string slices. We're going to be doing index of, right? So we're going to be doing a linear search for a given character. And, sort of the icing on the cake where they're going to recur, potentially. And that's how we'll basically handle all of these sort of border issues and edge cases. So the problem here, right, is it really can be quite expensive to do all of this just to find an adjacent node. And well, is there a way we can overcomplicate this to get better performance? And well, of course there is, right? Otherwise this presentation would have ended. And just to sort of take a step back, how do we actually encode a Geohash? This was something that was sort of glossed over at the start. Well, here it's going to be really helpful to sort of go through an example of how concretely this works. The way it works, as I mentioned previously, that it's a series of recursive subdivisions. So first we take a look at the X dimension, and we see that it's left of the first subdivision, and therefore we give the first bit a value of 0. We do the same for the second bit, and the same for the third. And it's going to be the same case for the Y dimension as well. To do another example that's a little bit less trivial, we repeat the exact same process. So we look at the first recursive subdivision, which is just going to be in the middle of the map, we see that it is left of the first subdivision, so we assign a 0. We go to the second value, we see that it's actually right this time of the second subdivision, so we assign a 1. And then finally, we assign another 1, now that we see that it is, yes, right of the third subdivision. We're then going to, according to Geohash, zigzag encode these bits. So we basically alternate longitude and latitude, or x and y, bits, one after the other here. We're going to get 5 here, right, which checks out with our Geohash of 5. But what if we actually avoid this final step and leave the x and y components separate? Well, on first look, it's not very interesting, right? We get 0, 4, 2, 6, 1, 5, 3, 7. It's not very easy to make sort of any kind of statement about these, right? It's not very useful. But an astute observer here, right, might look now at the x bits in particular, and you'll notice something interesting, right? Which is that if we simply flip the bits here, we get something that's actually quite nice. We get 0, 1, 2, 3, 4, 5, 6, 7. Okay, awesome. This is something we can actually use, right? And this gets us to the solution for our sort of fast neighbor lookup, which is, instead of concatenating the geohashes into a string, we can instead store these sort of otherwise zigzag encoded longitude and latitude bits into separate x and y geohash index keys. Hooray, right? There's no more variable length strings. We just sort of set a max geohash level, and we use that to drive the size of our integer index keys. However, we now need to encode 2 values in x and y, and we've lost a little bit of information. Before, the length of the string sort of was used to denote what the current prefix is. Here we've lost that information, so we also need to somehow know in a given context what the prefix is, the prefix length is, and what we are relative to. The good news here, right, is that you can almost always know this from the context. So in our code base, we actually almost never store this information. It's basically just inferred as a third property into any function. And, right, you'll see something here, which is that at the start, we mentioned how Geohash is basically just a kind of power of 2 grid. And we've basically just reshown this here, too. Basically, it's nothing too interesting. It's simply that you have a grid, and therefore, of course, you can find some way to index it in simply these sort of like a row column fashion. And when you index the grid in that way, it becomes completely trivial to find a neighbor, right? And, sort of just to reiterate how exactly this works, we can see that we can interpret the first n bits of a given x and y key to construct a relative grid for any given geohash level. So, at geohash level 1, right, we can see that the integer space, right, is going to be 0 to 3 for the y dimension and 0 to 7 for the x dimension, right? Here, right, we can see that we're going to start at 0 to 3 for just this first cell. And if we go a little bit further, right, we go back to our original example, we can see that that sort of relative indexing is going to carry over. We're going to start from 4 and go to 11 in the x dimension for these 2 cells combined. And, here we see that to find the neighbor, it's completely trivial. You just add 1. We go from this situation we had here, where it's very difficult and opaque to determine, the relationship between 2 very close geohash cells, to a very simple indexing system where you can just offset by 1. And so here we really have the best of both worlds. We still have sort of this arbitrary precision spatial indexing that we can build a prefix tree off of, and that we can use to do these sort of arbitrary precision, more or less detailed spatial indexing queries, depending on how zoomed in we are on the map. And we make it simple and fast to find neighbors, right? There's no need for these string operations. There's no recursion here. There's no, table lookup to find, which prefixes correlate to which other prefixes and which prefixes are on the border. And so I think the real key takeaway here, right, is this sort of power of 2 encoding. And while Geohash is also kind of, in a sense, a power of 2 encoding, in that it is going to be these sort of recursive subdivisions, which each subdivision divides something by 2, right? We end up with a grid. Geohash is really sort of just this idea that every level is going to be 5 of these recursive subdivisions, 2 or 3 for the longitude or latitude, alternating depending on which level of detail that you're looking at. So that really extends to a number of different things. And it's not just Geohash, right? You could do sort of these relative grid space computations, relative grid space, spatial indexing for a variety of problems. So that brings us to the end of the presentation. Thanks for watching. We hope you enjoyed this under the hood look at the JS API. But before you go, make sure you click that feedback button at the bottom of the video. We do use that information to improve sessions from year to year, so make sure you click that before you go. We hope to see you all in person next year, and again, thanks for watching.
Hi, welcome to this Q&A about ArcGIS API for JavaScript under the hood session. I'm joined with Matt and Yaron from the team. So before we start on the Q&A part, we have a few questions. I added one last poll. We added this session last year at last year's Dev Summit, and we try to find topics that are interesting to explore, that can be eventually useful for to you. And yeah, we would like to know if you have topics, questions that you have about the API, how it's engineered, and that we could explore, for example, for next year, for next year's Dev Summit. So I have a first question, maybe let's go with question about, can you pass the local to Esri widgets in the JS API? So yes, let me share my screen and we'll go to the SDK. Share. So I hope you see my screen. So when you are in the API SDK, in the overview page, you can scroll to the reference guide. And here you have a localization topic.
Don't know if you're seeing your screen, John.
In here, you have the details about the localization. So once you imported Esri ENTL, you can just call setLocal to the local that you want. You can specify the language and the I forgot the like the country, and then automatically after all the widgets, they listen to that local change and they react and reload their message bundles. So like that, you can switch dynamically at runtime the local used by the API widgets. So it's something that we added recently in 4.16. So maybe some widgets, we have to go through all the widgets and make sure that they react correctly to local change. If you find any bugs, please let us know. But in general, it works. So you can also define either you call setLocal. I recommend doing it at the beginning of at the boot of your application. But you can also define a global Esri config property with the local that you want. We used to use Dojo, and then we finished the migration to this in-house solution in 4.16. There are also more info in the API reference. If you go to Esri ENTL, and then you will find information on setLocal. You can be aware when the local change on the API. So you can subscribe your callback using the onLocalChange callback. And you can find also which is the current local that the API is using. So, and we explain here in which order we honor the local. So if it's defined on Esri config, we use this one. For backward compatibility, we use the local if it's defined on the global Dojo config property, or we use the language navigator language that is defined on the navigator object. In 4.19, so there is also some information about how the functions that the widgets use to be localized. Create JSON loader and so on. But we are improving the documentation in the upcoming 4.19 release. But yes, in this, you have all the APIs to fetch a message bundle, to register a bundle loader if you want to use this API to localize your application. The rule, though, is that if you have a framework that has a localization solution, you should prefer this one over using the API. But yeah. Yes, let's move on to a question for Matt. How do the cluster grid, Geohash, handle different projection? I assume it is not a one-size-fits-all solution. Does it also use the finding neighbor approach?
Yeah, sure. So great question. So in terms of the way the clustering works right now, it's really designed primarily for Web Mercator. But when you think about Geohash, right, that's going to be in longitude and latitude. So theoretically, that can work for a variety of projections. Where it does get difficult is with respect to the cluster grid, right? So right now, the API for clustering takes in a cluster radius that's specified in terms of pixels. The problem with that, though, is depending on the projection, pixels is going to be different. Depending on where you are in the map, in terms of like just the width of how long, in terms of the map units that correspond to that cluster radius. So, the long story short is the projection story is not quite there yet. It's something we're actively researching. In general, for projections where angles are preserved, things work fine because the calculation for determining, like what's right of this cluster cell still works. For projections where it's not, we run into issues, and we're sort of still in the process of deciding, like, what should the API look like? Should you say, cluster in a certain projection and then reproject the result of those clusters into, the new projection? Or do you want to actually try to do the clustering in the new projection without reprojection, right? So that the cluster radius in terms of screen space is preserved. There's sort of a lot of open questions here. And I think for us internally, we're going to probably try out a bunch of different approaches and see, work with our cartographers to see what approach sort of works the best. But great question.
Thank you, Matt. Next question. Can you briefly explain how Esri is harnessing the power of WebAssembly and WebWorker in JS API? So early on, we wrote our own, we needed to write our own rendering engine for vector tiles. And this is how the WebGL engine started. It was first by vector tiles, then we added feature layer and all the other layer types. But we are dealing with a massive amount of data, and to not block the main thread when we are processing that data to transform, whatever we download to the WebGL content, we decided to use web workers. Web workers by themselves, it's a very low-level API, and it's not very easy to use. And also we wanted to be able to load code dynamically at runtime because we use that for vector tile layer, but then we use also the worker framework for feature layer, for imagery layer, for I3S decoding, and so on. So we built a whole worker framework, and the worker framework is actually documented. It's in Esri core workers. So there is, if you want to check the under the hood session, I went more into details about the worker framework. There are other libraries out there, Webpack plugins, Webpack plugins, for example, that facilitates using workers. But yeah, it's really useful for us. The only downside is that if you have a very extremely heavy operation, maybe that might block other layers from working. But at least for a few moments, but at least the app stays responsive while the worker is working. So that's nice. For WebAssembly, we are using it piecemeal, just for very computational intensive work. Currently, we are using it for our I3S decoder and also for the projection engine. So that's the advantage, is that we can take the projection engine C code from Esri and then compile it for the JavaScript API without modification. So we don't plan to transform the entire API as a big WebAssembly blob because it's not we still need to marshal information between the JavaScript code and then WebAssembly. So it's not it's not good for everything. But for this particular use case, it's a black box. It works, so that's nice.
Maybe we can add a quick word on that. That we have been investigating using it. One of the things that Jan mentioned is the marshalling that is to go back and forth. So we look at the granularity for using WebAssembly, trying to assess the use of it. We have some internal let's call it tests that we ran against it. But yes, we are considering for it, and just like Jan mentioned, it's as we go along, what makes sense, we do for it.
Cool. Do you want to take the next question, Yaron? Details and architecture of the API.
Yes. So okay, sorry, I missed that. So this is an area that we actually already started. We did a kind of thorough work. As a matter of fact, Dario from our team did a really thorough work on documenting the internals, and whether in terms of the architecture, some of the methodologies and technologies we're using internally. The initial thinking was to either release it as a series of blogs, or maybe even talk about it during SIGGRAPH, etc. The thing is that things are moving so fast so that the doc itself cannot catch up with the actual changes we're making. And with this, so we have to go back to it. We will try probably to release at least part of it. As I think, in my opinion, probably a blog or a series of blogs would be the proper media for that. But yeah, we try. It's just that things are moving fast, so fast for us, and it's hard to kind of bring the doc to a point where it is aligned with where we're at in terms of the code base. So yes, something that is on our to-do list. It's something that we're aware of.
Okay, so let's move on to another clustering question for Matt. Do effects get applied when a feature reduction cluster is set? For example, to emphasize a cluster that has more than X feature.
Sure. So the way that works is that layer effects do get applied. Those are specified on the feature layer itself, but for feature effects, which are specified on the feature layer view, those currently do not get applied. And the problem here is that is sort of really the parallel with the feature filter. So when we designed the clustering, we wanted to make it really fast, specifically for the feature filter, so that if you're filtering data, you have the cluster sort of like immediately update on the map as you change the filter. However, right, there's a bit of a weird semantic here where, okay, feature filter applies to features, but then feature effect, does that still apply to features, or should that apply to clusters? So the real sort of limiting factor here is kind of on the spec side. We need to determine, what is the proper way to allow users to specify, a feature effect that is on clusters. Is that a cluster effect, right? Is that on feature reduction? Dot effect, so the answer is it's something that we really want to do, and we're sort of still going through the steps of thinking about how we could bring that to the API.
Yeah, thank you, Matt. There is actually another question for you. The clustering mechanism, including finding neighbors by Geohash indexing, is used on the client side, right? Meaning that the massive amount of feature has already been downloaded before, where we still could get into trouble with max record count.
Okay, I think I see what this question is asking. So the difference between 3x and 4x is that 4x can handle a lot more, can handle downloading a lot more data. So we don't run into the feature count issues because we will actually, when we request tiles of features, we divide that tile into a list of pages, and then we download each page. However, if you have 2 million features the clustering actually does still work in that case, but it can take quite a long time to download all that data. So, you know, we are looking at extending the clustering to support server-side clustering. So that's something that is currently in development. And we're hoping to be able to start prototyping that this year and hopefully be able to ship something for that as well.
Yeah, that's why what Yaron was saying is that, you know, it changes all the time. Like the Matt did a lot of improvement on the performance for the feature layer, and had to completely refactor how the web worker that is used for feature layer was done. He rewrote everything. So completely, you know, between like 4.19 and 4.16, I guess it's a completely different web worker, just because like that we can, you know, improve the performance.
By a lot.
You know, so it's going to be the same for server-side clustering. Probably there will be like some changes and so on. So it's hard to keep up for us to maintain a document on how everything works. But yeah, we have so we had a question about like GitHub repository for the code sample. I answered the question. I posted the link to the GitHub repo. The links will be also in the slides. We have I have the examples about localization, and then Yaron has his custom layers, custom feature layer with effects. There is another question about clustering that comes in. Yes, so clustering is supported for all feature layers. So client-side feature layer, but also GeoJSON layer, CSV layer, and what like OGC API feature layer, and yeah, and more in the future. We have a question about localization. If we have any custom widget library we ship to multiple apps, relying on the Forex API, what is the best way to use the new T9N translation and internationalization framework? So, so at Esri, we have you know, template apps that you can create using from the map viewer, and also the map viewer is using Dojo 18N. The map viewer actually is moving to the new API framework, so that they don't have to rely on a third-party API for it. But yeah, I suggest it's because, you know, they build everything using the API widgets. If you are using a framework that has, if you are using Vue or React and so on, Ember, whatever framework, you know, there is already probably like some localization API for it. I suggest to use that instead. It's really, for us, since we didn't want to rely on any framework because we just removed Dojo, we didn't want to use anything else. We had no choice but to create our own solution. So there will be more details how to use our API. We are not, you know, building an API for localization. We are building a GIS API, but as part of that, we need that aspect of it. So yeah, just yeah, check out for 19. There will be more details about it. And I think we covered all the questions. Yeah. Thank you very much.
Thanks, guys.
Thank you, guys.